There we go. I just don't have a video of this lesson, and I can send it to people who are absent. All right, so a couple housekeeping things before we get rolling, and this is for everybody. Tests, I am going to continue to chip away at those. I have a meet after school. That being said, I don't think it's going to be super long. So there's a chance I'll get to them tonight. Tomorrow is definitely not looking good. So if you don't see them posted by tonight, they will definitely not be posted till Thursday. Okay. I'll try to get those up. Everything else except for your test and your airbag lab, the exploding stoic bag labs, those should all be in the grade book. So make sure you're getting credit for all of the things that you are turning in. All right, and make sure we're staying on top of our work here in the last 3.5 weeks. We're starting to hit the home stretch, all right, which is welcomed, I think, for most. All right, so the last month, we've really been focusing heavily on one type of phase of matter, gases, right? We did gas laws. We learned about pressure and volume and temp, right? And then we learned about measuring them. And then we learned about how they were related. We did those scenarios. We learned about kinetic theory, about particles bouncing around, right? And all of that stuff. And then we went into the heavy math stuff, right? Which you guys just took your test on Friday. What we're going to come back with are the other two phases, right? We're going to talk about solids and liquids. And the good news is there's a lot of similarities. There is kinetic theory with solids and with liquids. Right? There are attraction forces and repulsion forces with solids and with liquids. The good news for some of you who aren't huge fans of the math is you've already done the math end for the most part of solids and liquids already. Our stoichiometry stuff, when we were doing grams to moles, mole to mole ratio, moles to grams, that's how you do the stoic stuff with a solid. We'll have to do a little bit of math with heat, but if I had to percentage this chapter, we're looking at like 80% not math and at most 20% math problem. Some of you, that is kryptonite for, because you learn how to do the math problems in class, you can solve them and you don't have to study, all right? And that is bad for you because you have a habit of not studying, and there is a lot of factual information in this chapter. And so you're going to have to make sure you know your factual stuff, right, in this chapter. For those of you that struggle with the math, this could be a good chapter for you. You can dive into the packet, you can learn the stuff, you can memorize some stuff, and you can succeed on the test. So everybody learns a little bit different. Okay. All right. So if we are going to look at this stuff, at the start of a chapter, I always like to recap some of the things that we have done and some of the things that we still have to cover. And at the beginning of the year, I said I wanted to fundamentally cover 6 things about chemistry. 3 of them are called classes of matter. 3 of them are called phases of matter. Classes of matter are things like elements. At the beginning of the year, we talked about elements a ton. You guys learned that elements are made up of these tiny things called atoms. An element, they're all the same type, right? You take your gold necklace, it is made up of trillions upon trillions upon trillions of gold atoms, identical, just repeated over and over again, stuck together. You guys learned those atoms have protons, they have neutrons, they have electrons. All right? You learned where those electrons and protons live, nucleus versus the electron cloud. Then we had a chapter where we learned where in the electron cloud we lived, and we learned about orbitals and energy levels, and we wrote configurations like 1s2, 2s2, 2p6, right? And that was all about where are the electrons living on the outside of the atom. Then we learned about some properties that atoms possess, right? How strong is their nucleus? It controls their size, their radius. How much do they like their electrons, electronegativity and ionization energy, characteristic traits that atoms have. And that pretty much fizzled us out on everything we could learn individually about an atom. So we graduated. We went on to compounds, right? And we said, okay, what happens if I take one atom and I put it with a different atom, right? We form these things called compounds, and we learned their types. If I take a metal with a non, I get something that's ionic. It has certain characteristics. You guys learned how to name it. No prefixes, symbols and charges and cross. We still do it, all right? We learned if the 2 atoms were non-metals, they form a covalent bond. You guys learned how to draw pictures of those covalent bonds. Bless you, and I'll recap that in a big way in the video you watch next chapter as a reminder. All right, we learned how to name them. They have prefixes, and we write what we see, and that stuff hasn't gone away. Then we learned what happens if I take multiple of them and put them together for a reaction. And you learned how to predict what the reaction was going to be with those elements and compounds and how we get new substances. All right, and we then went on to calculate the amounts of those substances with stoichiometry. So you guys have done a lot with elements and compounds. But the third class of matter is mixture, which is yet to come. We really haven't talked too much about mixtures in that term. But one thing I'll tell you is a mixture is simply a mix of elements and compounds where they keep their properties. So if you know about elements and you know about compounds, you're going to learn about mixtures quick because you don't really change anything. You just mash them together. It's not a reaction. Then our phases: solids, liquids, gases. We have talked a ton about gases. All right. We have not talked a ton about solids and liquids. That's what this chapter is all about. We're going to learn about our solids and our liquids. Now, a lot of the things that liquids and solids do and why they do them are controlled by these things called intermolecular forces. That's the video I'm going to have you guys watch of me teaching first period next class. Okay. For this class, we're going to talk about the what to do. So we're going to fast forward to slide number 12, which gets us here. Our properties of liquids. And so take a second, get yourself there. All right, and you guys learned properties of gases. You had a test on it, right? I set up stations, all right, for you to help remember some of the things gases can and can't do. For instance, when I lit the ramp on fire, what were you learning about gases? Fluidity, that's a property of a gas. All right. Whenever you were up front pushing on that syringe up here, what were you trying to learn about? Compression, that's a property of a gas. Right. Whenever I would bring up the piston chambers and I'd open it up and you'd see them spread out, you were trying to learn about expansion. That was a property of a gas. Liquids have them as well. Some are the same, some are different. All right, here are some of your properties of liquids. All right. First of all, liquids get defined as anything that doesn't have a definite shape, but does have a definite volume. Here's what I mean by that. You take my coffee cup, right? Currently, all right, if it is filled to the max, what is the shape of the liquid in my coffee cup? Cup shaped, right? If I poured that liquid into a beaker in the back, all right, take a guess at how big this cup is. Yeah, pretty big, right? Do you think it would fill like a 600 milliliter beaker? Brian says, yeah. Fair enough. Let's say it filled it perfectly. So there's 600 milliliters of liquid in here, and it's cup-shaped. Right. When I pour it into the beaker, how much liquid is in the beaker in terms of amount? Is it still 600 milliliters? Yeah, right? The amount of liquid didn't change because the container changed, right? But what's the shape of the liquid now? Beaker shaped. What if I took that beaker and I dumped it onto, a tray from the cafeteria, right? What shape would the liquid be? Tray shaped, but would it have 600 milliliters of liquid on the tray? Yes, that's what definite volume is, that no matter what the canister holding it is, it takes up the same amount of space, right? 600 milliliters. But the shape of those milliliters can change. Yes.
Would it really be 600 milliliters though? Because how when you dump something out, you still got that stuff on the side, it doesn't all come out. So would it really be 600?
So assuming I had a complete transfer, yes. But like you said, if some of it got stuck to the container, I would lose a little bit. Yeah, absolutely. All right, so liquids possess these properties, and they also are known as fluids. All right, so liquids and fluids, we use those terms interchangeably. All right, here are the things they can do. All right, 5 characteristic properties of liquids, and we'll go through them one by one as we go through class. All right, but the first, liquids have high densities. That's similar or different than gases? Different, right? What type of density do gases have? Low, which is why when I put a gas in a liquid, what direction does the gas go? up, right? But if I pour a liquid into a gas, like if I dump my coffee into the air, where does the liquid go? Down, because it's more dense than the thing it's surrounded by. All right, so liquids have high densities. You'll learn why here in a minute. Liquids are incompressible. What's that mean? You can't squish them. If you want to test this theory, go up to the 10-meter high dive, dive off, spread your body out, and when you smack the water, is it going to feel like the water compresses very much? No, right? There's a fact that they teach in diver training, for the Coast Guard. They say that if you jump out of a helicopter at 100 feet, all right, at that height, and you fall and hit the water, it's the same as hitting the ground, because liquids don't compress that much. So when you have that amount of distance to fall, hitting the water is basically the same as hitting the ground. All right, so because liquids don't compress, all right, very much. Diffusion, right? Gas is diffused. What was diffusion a fancy term for? That's expansion, but when two spread out and then they run into each other, they mix. So diffusion is mixing. So it's two gases expanding. All right, so diffusion is mixing. Can liquids mix? You bet, right? I'm going to show you some examples. Here's a new one, surface tension. Part of the reason that your skin stings when you flop off of a diving board is because you are attempting to break the surface tension of the water, right? If you look at the water, when nobody's in it, does the water look like it's waving or is it really still? Still, because believe it or not, when you're not disturbing the water, those surface molecules form connections and they grab onto each other. So when you try to dive through that, you are breaking those connections, right? And that's why it hurts when you guys fall off. And then the last big one, which will get us into phase changes, and then I'll get Ryan's question, is vaporization, all right? When liquids turn to gas, they call it vaporization. It comes in two forms. The first form is when I force it to happen. What do we call it when we force water to turn to a gas? That's the second one. Boiling. Boiling is when we add heat specifically to a substance, purposefully making it turn into a gas. The second one, Ryan, was evaporation. This one occurs naturally from the heat due to the air and the sun, and the molecules on the surface of the liquid get to turn into a gas. So when you boil something, any molecule inside the liquid, top, middle, bottom, they can turn to a gas and leave, which is why you see the bubbles. But when we evaporate, it's like peeling an onion. You have to take the first layer, then the second layer, then the third layer, because evaporation only happens on the surface. What was your question?
Like, wait, you said like the little waters from each other. How can you get through it? And like when you're underneath, how can you get back up? Like, why don't you get stuck?
Luckily for you, your weight and your strength of being able to swim exceeds the strength of those forces, right? So when you hit the water, you break those forces and you will be back up before they, A, would have time to reform, and B, if they did have time to reform, they're not strong enough for you to punch through. But there's times that they're not. When can't you get back up from under the water? But not because of fatigue. Like, why do you not want to fall through the ice? Because you can't get back through the solid. So when the forces form and it gets to be a solid, the forces a lot of times are too strong for you to like punch back through. But luckily for us, the forces in a liquid aren't as strong. You can like punch your way back up through the liquid. All right, and these are all great questions. Right, great questions. All right, so I want to attack these one by one. All right, first one, high density. Definitionally, high density says that at normal pressures, liquids are 1,000 times more dense than their gas counterparts due to how close the particles are. All right, take a look here. A high dense substance, they're all jammed together, really close. The low dense substance, they're spread out like gases, far apart. You guys experience this every day without knowing this. When you're in the shower and you take hot showers, what does the shower fill with? Warmth, and you can see it. You can draw on your mirror because of it. Steam, right? Steam is gaseous water. All right, now, when you turn the shower off, does the steam stay there for forever? No. Eventually, what do you see on your shower door? Water droplets. Was it there while you were showering? No, because what happens is as the temperature lowers, those spread out particles find each other and they connect to each other. They form forces. And when enough of them bind up, you create droplets, right? The droplet is super duper tiny compared to the steam that took up the whole shower, right? So that's why an entire shower full of steam can condense into, 50, 60, 70, 80 particles of water that's on your glass door of your shower. Okay. All right. When you're talking about liquids, all right, liquids are close, but they're not stuck. All right. So you have two liquids touching each other, but they still have the ability to move. So I'll use this guy a fair amount in this chapter. Right now, you are looking at a solid. The reason I know is if I do this, what didn't happen? Things didn't fall off, right? The forces were so strong that they didn't go anywhere. That's a solid. Liquid's a bit different. They're still touching each other, but they have the ability to move. That liquid can roll around, and if I tip it, it will fall. Right? So liquids are touching, they're in contact, but they can slide by each other. These particles can sneak by each other. All right? That's the difference between a liquid and a solid. But think about it. Who is the liquid more like, a solid or a gas? Solid, right? Because the solid particles are pretty close together as well. The gases are all spread out. So a lot of the characteristics you see in a liquid are a lot like a solid because at the particle level, liquids are a lot like a solid. There's very subtle differences. All right, so we'll talk about this guy fairly. Why does this happen? It's because there are forces of attraction that hold these things together, and it's a little bit stronger than the forces that are trying to push it apart. Things that hold stuff together are called IMFs, intermolecular forces. That's a bunch of what you're going to learn next period. All right, the stuff that tries to break you apart is kinetic energy, which is often provided in the form of heat. Okay. All right, round two. All right, if we're talking about liquids, all right, and we're talking about the high density of liquids, this is always a fun experiment to do, and I set it up this way so the people at home can participate as well this time. What you see here, right, is a big graduated cylinder, and I have put 4 substances into it. I have put water, I have put cooking oil, I have put alcohol, and I have put a substance called glycerin. Now, there may be food dye involved in some of these. I'm not going to make it easy for you. First thing you see is, are these guys mixing? No, and because they're not mixing, I know fundamentally these substances are different from each other. You're going to learn that one segment of them are non-polar and one segment of them are polar. All right, which you'll learn what that means again next period. What I want you to do, all right, is try to decide which substance is which color based on your own life experiences. If I am going to mix water, oil, alcohol, and glycerin, right, how do we think that those guys will layer? All right, so take a song and just write in your packet, sketch down, all right, what your order is, and then I'm going to start picking the brains of you guys and see what we come up with.
Last night out of the blue, drifting off to the evening news. She said, honey, what would you do if you'd have never met me? I just laughed, said, I don't know. I could take a couple guesses though, then tried to dig real deep. Said, darling, honestly, I do a lot more offshore fishing Probably eat more drive-through chicken. Take a few strokes off my golf game. If I'd have never known your name, I'd still be driving that old green Nova. I probably never would have heard of yoga. Be a better football fan. But if I was a single man, alone and out there on the loose, I'd be looking for a woman like you.
Okay, not needing the whole song for that. All right, so if I go to my next slide, all right, we're gonna go ahead and put some orders out there. I've made a big collective, all right, down here, whoops, that I can drag out as I need it. All right, so Janie, talk to me about who you think is the purple, who do you think is the blue, who do you think is the yellow, green, who do you think is the red? All right, so Janie has the water here. Okay.
And I have the oil as the red one.
Oil as the red one up top.
Yeah.
Okay.
And then the green one is the glycerin.
And the blue one then?
Yeah, blue is the alcohol.
The alcohol. Okay. All right. Picking on somebody at home. Nina, talk to me about what order did you have? Go ahead and list them from like top to bottom for me, and I'll drag them.
Okay. I had alcohol on the top.
Okay. Yeah, just keep saying.
And then I had glycerin. And then oil and water.
Okay. All right, get a couple more. All right. How about Adriana? All right. What order did you put yours in? Up on top. All right, so she said glycerin up top. And who? Then water. Then alcohol. And then oil. Okay. All right. Grab me somebody else at home. Jason, how about your list?
I had oil, alcohol, and then glycerin, and then water.
Okay. All right, let's snag one. In person, Ethan, what'd you come up with?
For red, I had water.
Okay.
Yellow green, I had glycerin.
Okay.
Blue, I had alcohol, and purple was oil.
Okay. All right. It looks like I could probably squeeze one more in. All right. So how about Samantha? What did you do for your list?
I had water at the top. And then alcohol.
Okay.
And then glycerin.
Okay. And
then oil.
then oil. Okay. All right. So as I scan these lists, kind of a mixed bag. All right. So and this is for anybody, if you had the very first list, oil on top, glycerin, alcohol, water, just start talking to me about why did you layer certain things certain ways, Jay?
I just put water on the bottom because it's placed in
And because it's not, you're assuming that?
oil in it.
Okay. Why did you have the oil above the water?
Just because water, I thought that the water would mix with them.
Okay. Right. So there's two components to this. Janie's saying we know some things mix with other things, and she knows, listen, oil and water don't mix, right? Which means they would have to be layered near each other, right? And they would still be okay. But if I'm like the water, I will mix with it. Anybody ever seen an oil spill, like on TV? Right? Where's the oil at? On top of the water, right? So if I were going to try to use a life experience for this, I would be putting the oil above the water. Now, I don't know where on the list they are, but my life experience tells me when there's an oil spill, they got to scoop it all off the surface. They're worried about all the birds, right, that are landing down in it that could catch on fire, and then it's all burning on the surface of the water. All right, so the oil should be above the water. All right, now, the next thing is we need to separate things that we know mix with each other. All right, so scan your list. All right, what are two things, right, from your life experience, hopefully not too much, or hopefully from watching your parents, that you know mix? Alcohol and water mix, right? We know that because when you pour, a beer out, it looks like one thing, and the beer isn't 100% alcohol, right? Right? Beers are like 5% alcohol. All right, so we know that those two substances mix. So if I put the alcohol right next to the water, what would it do? It would mix, and I would just get one big phase, right? We would know they would mix with each other. So because they don't, I know the alcohol and the water have to be separated, right? So the alcohol and the water have to be separated, and we know the oil's got to be on top of the water, so things are starting to get a little bit more clear. If I would let you have one piece of information to look up about each of the substances, what would you guys look up? You would look up what it is or what about it? So he'd want to know if the glycerin mixes with it. I would tell you glycerin does not mix with water, all right? Which means what will it mix with? Oil. So now you know oil and glycerin can't be what? They can't be next door. And you know that alcohol and water can't be next door. So you know those have to stagger, right? It's got to be like oil, alcohol, glycerin, water, right? They have to be staggered. What else would be useful in terms of determining the order that they layer? And what controls whether you float or sink? So if I gave you the densities, do you think it would help you? Okay. There are their densities. All right. Now take like 30 seconds of this song, and with the numbers, I'll give you another chance to order them. Go ahead.
Well, I could tell that got her attention. So I said, oh yeah, I forgot to mention. I wouldn't trade a single day. 400 years the other way. She just smiled, rolled her eyes. She's heard all of my lines. I said, come on, girl, seriously. If I hadn't been so lucky, I'd shooting pool in my bachelor pad, playing bass in my cover band, be stocking up cold Bud Light, poker every Tuesday night. I'd have a dirt bike in the shed, not one throw pillow on the bed. I'd keep my cash in a coffee can. But if I was a single man, alone and out there on the loose, I'd be looking for a woman like you. She knows what a mess I'd be if I didn't have her here. And to be sure, I whispered in her ear.
Okay. All right. Anybody feeling confident about their list now? All right. Michael's shaking his head. Michael, who did you put in red at the top? How about the yellow, green?
Oil,
Followed by?
water,
Followed by?
glycerin.
Why that order?
Glycerin has the largest density, so I imagine it goes with oil.
So Michael's saying that the more dense you are, the more likely you are to sink. How many people agree with that? I agree with that as well. All right. So if we look at this guy, all right, the alcohol will be on top, which I did put red food dye in. The oil, all right, that ended up being actually the way it was. That yellowish was just pure cooking oil. I didn't have to dye it. The water, I put blue food dye in, and that's why you're seeing just a little bit of green, just because I have a yellow and a blue right next to each other visually. So the light is hitting them both a little bit. So that's why you see that tinge of green. All right, the water had blue food dye in it, and then the glycerol had purple food dye in it. All right, so your take-home message is here. Liquids organize from the most dense on the bottom to the least dense on the top. All right, liquids layer or mix based on what we call solubility, meaning like mixes with like. So two of the substances are what we call polar, which we'll talk about, and two of them are called non-polar. So here's the million-dollar question. Imagine I put a really long stirring rod in here and I stirred it all up and shook it and let it settle. What do you guys think would happen? You think it'd go back to all four phases? How many people agree with that? Okay, how about a counterpoint, a different idea? All right, Ash? All right, so Ash thinks like if we mix them up, the ones that would mix, and then when they separated, we'd be down to just two colors. How many people agree with that? Yes, I agree with that one as well. When the two substances that are alike find each other, they will dissolve in each other, creating one layer. All right, so for me to do this, I have to pour it in a layer at a time. I have to pour the glycerin in with the funnel. Then I have to come in, I have to pour the water in slowly with a funnel, then the oil, then the alcohol. All right, because otherwise, when those similar phases touch each other, they will blend. Okay. All right, questions on densities of liquids. All right, that's a good place to take a break. Why don't we take 5? And when you guys come back, we'll round out some of the other things we know liquids can do. Set a timer for 5 minutes.
Your timer is set for 5 minutes.
So my sister-in-law is an Australian citizen, and my brother and her live in Australia, so it's a subtle reminder that I should reach out and talk to them from time to time. I try to do a little. Is there a multiple ratio? Somebody over here was struggling with a problem, and I just showed it. What was that? Yeah, that might have been you. Was I helping you with the problem? That's right. Yes, sir. The chemical equation, you bet. I have no idea. We have no problem. The school isn't given a problem. That's like paramount. So I don't know what it is. 21st. You need one. They did. It was over at the that's it. It was I think freezing cold. Yeah, that's up to code. That is a good old Steve decision. Cassandra, when do you leave for your trip?
May 25th after school.
So about 2 weeks.
My dad's still not sure
Thank you.
when he wants to leave. We might be like in the 24th.
Public service announcement. Anybody got an email from me about a 2-question survey yesterday? Please do it. If you didn't, it's just about my parking drive. Take you like 10 seconds. If you have a parking permit on file with the school, you got an email.
How long ago did you send
Sent it yesterday at like.
Oh.
You can just search my name at the top.
I thought my life was said roughly 2 weeks ago, but so how about we if you don't have a okay, you know how to get one.
I did not know that. That's unfortunate.
It turns out.
Did you feel like you were getting done really early?
Yeah, I did. I know.
She's like, I'm an all-star. These minions around me are taking all of that.
The one underneath the goggle cabinet should work, Michael.
But fun. I'll pass by it.
So yes, I'm using the problem fast. If you're the answer.
Yeah.
Indeed. I'm going to go back to teaching now. That's okay. I promise I'll make them answer your 2-question survey.
By the way, Caitlin Peterson answered yesterday that she had a Tesla.
Oh, nice.
And so I emailed her and I was like, do you really have a Tesla? And she's like, oh my gosh, Alex Super opened that and answered it on her phone because he liked Teslas. He didn't even read the question. I was like,
The thought that counts. At least they were trying to participate.
"Do not have a Tesla."
All right, and you go ahead and hit the lights for us. Just the front ones. Just the front ones. Perfect. Okay, so high density is one characteristic of a liquid. Let's look at some others. Second one that was listed was that liquids are incompressible. Why are they incompressible? Because their particles are close together. And if your particles are close together, the reason is there's a lot of forces of attraction that are in play. So if we look at a substance, take a look at your 2 chambers. The gases that are down here on the left, a lot of empty space between them. But your liquids are all nice and filled up. All right, the less space between particles, the more you trend toward being a liquid or a solid. So you're going to find out that attraction forces control a lot about how you look. The more attractive you are, the more you tend to be a liquid or a solid. The less attractive that you are, the more you trend toward being a gas. All right, third trait that all liquids possess is they can diffuse, they can mix. If we take a look, liquids and gases can both diffuse because, remember, are the liquids stuck in place? No, they can roll around, which is why if I put food dye in a glass of water, you can see the arms reaching out. You can see the difference between the blue food coloring particles and the water because light goes straight through the water, but it bounces off the food dye. So those particles, as they're moving through, because they're not stuck in place, weave their way among all of the other liquids. All right. So now here's kind of an interesting question, though. When you look at those glasses, and that was right after I mixed them, who is there more particles of, the blue food dye or the water? Who are there more particles of? The water, right, by far, because the water filled up the glass, and how much food dye did I probably put in? Yeah, like maybe 1, 2, 3 drops at most. So the $1 million question is, when I stir it, did I change the number of drops of blue food dye? No. Did I change the amount of water? No. But when I stir it, what's it visually look like? It turns blue. But if there's way more water in it than dye, why does it look like the dye? So it diffuses. All right. Keep going on that idea. Balances out. So let me ask you guys, if you're a food dye and at home, folk, you'll just have to imagine what I'm doing. Let's say I'm red food dye because I'm in my red shirt and you guys are all water. When I go like this and I'm food dye and I come over, man, touch your shoulder, and I touch Jamie, do I turn her into a red water molecule? No, right? When I move through and I touch Ryan, does he turn red? No, right? So dyes do not change the water to be red water cells. They're still waters. The reason why it looks all like the blue food dye is when you look at it, what do you see when you look at water? Yeah, you see through it, right? So what happens is when we evenly spread the dye out, I look through 1 billion water molecules and I only see the food dye that's buried in there. All right, so I don't want you guys to think that dyes change the color of molecules that they're mixing with. That doesn't happen. Okay? So that's a big idea. It's not a chemical reaction. They just mix with each other, and you just can't see what's happening there. All right, so if we take a look at this little simulation here, assuming it works. If I make this look like a liquid, say when.
What are we looking at?
Just when do you think this looks like a liquid? Sorry. When that looks like a liquid. Okay. Yeah, starting to trend toward looking like a liquid now, right? Let's do the same thing on the other side. Liquid. Okay. Okay. All right, so I have 2 separate liquids here. All right. Do they have the ability to move? Yes, they aren't stuck in place, but are they going very far? No. So if I remove the divider, what are those things going to do? They're going to start to mix, but is it going to be fast or slow? Slow. This is why mixing liquids is a slow process, but 2 gases mixing happens very quickly. So if I remove my divide, right, those blues and those reds have to like infiltrate their way into the tiny open spaces in between each other, which there aren't many because liquids are pretty tightly packed. This is what's happening when we mix. And eventually, if I let that keep going, what would you see? Yeah, it would be pretty evenly distributed. And if it was really red mixing with blue, visually, what would you guys see in the real world? Yeah, it would seem purple to you because the light would be bouncing off the reds and the blues and coming back to me at the same time. And those 2 wavelengths would merge into a purple for me. Right. Yeah, sure. Good. Okay, so this is all about diffusion. This is how substances can mix. All right, pivoting back. Surface tension. Surface tension was that idea that the particles on top of the liquid will connect to each other. Definitionally, it's a property of all liquids that pools adjacent. Sorry, geometry term. What's adjacent mean? Next to. The adjacent means the molecules next to you. So my next door neighbors. On the liquid surface together, decreasing the surface area to the positive. So we pull them together so they get a little bit tighter, right? So the surface of the liquid is just a little bit closer together, all right, than the rest, which is why if you look at that droplet in the picture, where is it the narrowest at? At the top, at the surface. Those particles are pooling tight together on the surface. Again, attraction is all about intermolecular forces, IMFs, which you guys will learn about. So the stronger the intermolecular forces, the greater the surface tension. All right, so I usually will do a demo like this, but again, we have people at home, so I'm just trying to keep it even. Where I have you guys see how many drops that you are able to put on the surface of a penny. So I had you take little droppers, and I had you put drop, 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 and count how many drops you could get onto the surface of an individual penny. All right, so I went ahead and did this with my kids at home. All right, Scarlett, my daughter, she was able to get 58 drops onto her penny. Gabe, my son, he was able to get 81 drops on his penny. Some of that is technique because in theory, what should be true? We would expect them to be the same, right? Now, are all pennies even? Absolutely not. Some pennies might be dirty. Some pennies might be clean. Some of them may have used the head side. Some may have used the tail side. And because the tail side has the Lincoln Memorial on it, it's got those little grooves, which in theory it could hold a little bit more liquid. The delivery is the biggest common factor, right? Why hers burst at like 58 drops is she was dropping from a little bit higher up to see the drop, and he got real close to it so that the penny didn't, or the drop didn't have to move very far. Because remember, the force that it strikes is going to be a factor as well. All right, so what's happening on the surface of those pennies is we're creating this bubble. And you guys see this in a glass of water too. You can like fill a glass over the top, right? It's because there's forces holding the top of the surface together. All right, so water molecules on the surface have fewer neighboring molecules, so the forces are the strongest. They don't have to share them. All right, so you get these binding forces right here. Right, the surface ones where the double arrows are, they connect the strongest, all right, and we can stack and stack and stack and stack more and more and more. But eventually, why does the bubble burst when we get to some number of drops, whatever it is? Right, what's going to happen for the bubble to burst on the penny? We break the surface tension. So if there's attraction forces holding it together, we overcome those attraction forces. What is it that overcomes those forces? What do we think it is that breaks those forces on the surface of the penny? The size of the droplet. And think about like when you're at the bottom of the ocean, why is there so much pressure? Because the weight of it, eventually the weight of all the water stacking will break the tension, right? Will overcome those forces, and then they all, fizzle out and drop to the bottom. All right, so that's the little demo on the penny surface, but you see this as well in liquid containers. It doesn't just have to be a liquid with itself. Sometimes I could have a liquid grabbing onto a container it's in, right? So if remember we collected our gas in that big skinny glass tube, right? How many of your groups had a curved bottom? When you read it, like the sides were just a little bit higher for the liquid than the bottom was. Did anybody notice it? Yeah, you should have, because they all form what we call a meniscus. All right, so we get two types, and Mrs. Sherry should have stayed because she would talk to you about this. I know she talks a lot about these last year. You've got cohesion, and you've got adhesion. Cohesion is water attracted to what? Itself. adhesion is water attracted to the container, to the glass. All right, so in B, we get cohesion because the water's holding to itself better than the glass, so we get a convex. In A, we get the meniscus because it's grabbing onto the glass more than it can grab onto itself, so it sinks in the middle of it. All right, so capillary action is a product of surface tension, and it occurs in a meniscus because it grabs onto the glass with better attraction force than it grabs onto itself. And the meniscus can be concave or convex, depending on where the attraction is. All right, so let's explain to you why it's concave. Right? It's more attracted to the glass than it is to the water. And in B, we're more attracted to ourselves than we are the glass. All right, and then this is just me summing that up on this slide about adhesion and cohesion. Last topic of the day, then I'll give you guys some time, all right, is vaporization. And a vaporization comes in two forms. It comes in boiling and it comes in evaporation, but basically it is simply a liquid turning into a gas. So when a liquid turns into a gas, it could be evaporating, which is just occurring at the surface, or it could be occurring throughout the entire substance, which is boiling. All right, so evaporation is the process by which particles escape the surface of a non-boiling liquid, and they just turn into a gas and leave. Boiling is when we get to change them all, right? We have added so much heat to it that they can overcome all of the attraction forces that hold them together. All right, so these are our what's, and next period you're going to learn why. All right, these things happen, these attraction forces. I'll do a big, quick recap on that. All right, so with the time left for all you guys, what I want you to do, all right, is the following assignment in the book, and this will be due tomorrow, or next time we meet. It's page 366. Numbers 1 through 5, and page 388. Numbers 1 through 3. Page 366. Numbers 1 through 5, and 388. Numbers 1 through 3. All of these will have to do with properties of liquids that we were talking about.